Hi, Year 12. Right, I'm going to make what I think will be the final video clip on the haloalkanes topic now. So I'm just going to share my screen with you and just show you briefly in your note packs which bits we're going to be covering. So in your note packs, you need to turn to page 12. So we're going to be looking at a new mechanism. So we've already done two mechanisms as part of the haloalkanes topic. We've done the free radical substitution, which involved the three stages: initiation, propagation, termination. We've done the nucleophilic substitution, which was your first curly arrow mechanism, where we can either have hydroxide nucleophiles, cyanide nucleophiles, or ammonia nucleophiles. So now we're going to look at our third mechanism, which is another curly arrow one, which is called the elimination mechanism. So I'll be reviewing this just like I did before on a piece of paper, sort of explaining it a step at a time in just a moment. We're then going to move on to some important points about comparing the elimination and substitution mechanisms, and then I'll be finishing off the topic talking about the ozone layer and how haloalkanes have a detrimental effect to this. So by the end of this video, we'll have covered all the information which is in the note pack, and I'll explain what tasks you can move on to. Before I move on to a piece of paper separately, I just want to highlight there is an error in your note pack. The mechanisms which are shown here, hopefully those of you who are on the ball with this should spot this already, the negative charge is in the wrong place. Really, on a hydroxide ion, the negative charge and lone pair should be over on the oxygen. So that technically would drop a mark in an exam. Also, the example underneath, that negative charge should be where the lone pair is also. So just wanted to highlight that for you. Okay, so even though we're moving on to a new mechanism, I'm actually going to start off by reiterating the nucleophilic substitution, because there's some key differences between these mechanisms that you have to recognize. If I take a haloalkane, so here I've got one bromopropane, and I react it with sodium hydroxide. We've already mentioned previously sodium hydroxide acts as a source of hydroxide ion. So here's my OH minus, negative charge, and lone pair on the oxygen. And in a nucleophilic substitution, the negative charge and the lone pair on the oxygen attack this carbon. This carbon is, of course, slightly positive because the bromine is slightly negative. And then we break that carbon to bromine bond in our second curly arrow to make our product. So in nucleophilic substitution, our haloalkane turns into an alcohol, and our byproduct is the bromide ion, which is kicked off, okay? And in that mechanism, the reaction conditions are aqueous. So that reaction has to take place dissolved in water. Now, the reason why I've reiterated that mechanism is because if we now want to do an elimination mechanism, we can take the same haloalkane, so it's still one bromopropane, we can take the same reagent, so it's going to be sodium hydroxide. I should highlight it could be potassium hydroxide as well. Either is fine, they just both act as a source of hydroxide ions. So I have hydroxide ions here, but in an elimination mechanism, a different set of curly arrows take place. Rather than the hydroxide ion attacking our slightly positive carbon, in an elimination mechanism, you look at the carbon that our halogen is attached to, so our bromine is here, that's the carbon it's attached to, and then we need to look at the next door carbon. And our hydroxide ion is going to attack one of the hydrogens on that next door carbon. It doesn't matter which one. So because my hydroxide ion is up here, I'm going to attack this hydrogen. So arrow number 1 is for attacking one of the hydrogens on the next door carbon. That gets you a mark in an exam. Arrow number 2, the electrons from this carbon to hydrogen bond here travel into this carbon to carbon bond. That gets us our second mark. And arrow number 3, the carbon to bromine bond then breaks and the electrons go onto the bromine. So that is your third mark. So this, just like our nucleophilic substitution, is a one-step mechanism. So there's no intermediate, it goes directly from the reactant to the product. So my product, the first carbon on the end hasn't got involved, so that stayed exactly the same. The central carbon now has one fewer hydrogens. This hydrogen has been taken off and it's now attached onto the OH, which we'll deal with in a second. So this carbon in the middle is still bonded to this hydrogen below. And because the electrons in this bond have now travelled into this bond, this carbon to carbon bond has now turned into a double bond. Finally, this carbon at the end has two hydrogens attached. It did have a bromine, but the bromine has been kicked off, so we can ignore that now. So we've now got those same two hydrogens attached onto that end carbon. So we have converted our haloalkane into an alkene. And if we look at our byproducts, just like last time, a bromine has been kicked off. So we have a Br- floating around. But also, because our hydroxide ion took a hydrogen off of the molecule, the OH and the H combine together to make water. So water is our byproduct. So the reason why this is called an elimination mechanism is because we have eliminated, we have removed things from this molecule. We've removed this hydrogen because it's attached onto here now. We've removed this bromine and it ends up floating around on its own as a bromide. Okay? Now, essential point. This reaction has to be carried out in ethanolic conditions. So we have to dissolve our haloalkane in ethanol. And there's a really important reason for that. Both these mechanisms involve the same haloalkane and they involve the same reagent, either sodium or potassium hydroxide. The only thing which is going to determine whether our hydroxide ion decides to carry out a nucleophilic substitution or whether our hydroxide ion decides to carry out elimination is the solvent that we carry out our reaction in. So the moment an exam question indicates that it's an aqueous reaction and it's dissolved in water, that's the big clue to tell you nucleophilic substitution is occurring. If a question indicates it's ethanolic conditions, it's dissolved in ethanol, that's the big clue to tell you that this elimination mechanism is occurring. So you just need to learn that. Following things they could also ask you are the same as previous examples that we've looked at. So they could ask you for the overall equation. So if that was the case, I'd be writing CH3, CH2, CH2Br plus my hydroxide ion. And it's going to make CH3, CH2 plus my bromide ion plus water. They could ask you the role of the hydroxide ion. In this one, it's nucleophilic substitution. This is acting as a nucleophile. In the elimination mechanism, the hydroxide ion is acting as a base. Remember when we looked at the ammonia mechanism, we said one of the ammonia acts as a base because a base is a proton acceptor. This hydroxide ion is accepting this hydrogen. So because it's taking a hydrogen off, this is acting as a base in this situation. So this is our new mechanism, an elimination mechanism, 3 marks for 3 curly arrows. Right, what I'd like you to do then is to pause the video here. I'd like you to have a go at carrying out the elimination mechanism on these 2 haloalkanes. So get a bit of rough paper, have a quick go at scribbling out the mechanism for what these 2 would look like, and have a go at naming the product, please. Okay then, right, let's go through those. So this first one, I've got 2-chloropropane. I'm going to be using sodium or potassium hydroxide, doesn't matter which one, they both act as a source of hydroxide ions. Now, my hydroxide ion has to attack a carbon, well, it has to attack the hydrogens on a carbon next door to our halogen. So remember, we find our halogen and see which carbon it is attached to, and we have to pick a neighbouring carbon. So here we've actually got 2 options. This is a neighbouring carbon, so we could attack any of these hydrogens, but also this is a neighbouring carbon, so we could attack any of those hydrogens. So of the 7 hydrogens which are surrounding this molecule, 6 of them are completely viable options for our hydroxide ion to attack. The one that you can't attack is this hydrogen in the middle. It needs to be on a neighbouring carbon. Okay, so let's say I'm going to attack this hydrogen here. So arrow number 1, I attack one of those hydrogens. Arrow number 2, the electrons from the carbon-hydrogen bond go into the carbon-carbon bond. Arrow number 3, we then kick off our chlorine atom, or chloride ion it will be. So by the time I've carried that out, my first carbon is now going to be doubly bonded to the second carbon. My first carbon now only has 2 hydrogens attached because that one's already been removed. My second carbon no longer has a chlorine, but it still has a hydrogen. And my third carbon has stayed relatively unaffected. That still has all 3 of its hydrogens attached. The OH group has now gained a hydrogen, so that's formed water. And the chlorine has now been kicked off as a chloride. So that is meth, eth, prop. This is propene. Okay, and it doesn't matter if we'd attacked one of the hydrogens on this side, it would have still formed propene, just with the double bond on the other side, same molecule flipped over. Okay, right, second example down here then, same idea. I need sodium hydroxide or potassium hydroxide to act as my source of hydroxide ions. I need to find the carbon where the halogen is attached. I need to find the next door carbon, so this time one of these 2 hydrogens can be attacked. Again, it doesn't matter which one. Arrow number 1 attacks the hydrogen. Arrow number 2 from the carbon-hydrogen bond into the carbon-carbon bond. Arrow number 3, we then break the carbon-bromine bond. So in this situation, we're going to have our first carbon to carbon bond is now a double because we've lost that and we've lost that. So the first carbon still has 2 hydrogens attached. We've then got 1 hydrogen attached to our second carbon because that one's been removed. And our third and fourth carbons are relatively unaffected again. So CH3 is attached there and a hydrogen, and then 3 hydrogens attached to that final one. So in terms of, let's finish it off. The OH has gained a hydrogen, so I need water. And my bromine has been kicked off as a bromide. So naming our product, meth, eth, prop, bute. So this is a bute molecule. It's got an alkene, so it's going to be bute-1-ene, but I've got a methyl group on carbon 3, so 3-methyl bute-1-ene. Okay, remember both of these would have to be ethanolic conditions, because if they weren't ethanolic, if they were aqueous, they wouldn't do the elimination mechanism, they would carry out the nucleophilic substitution mechanism. Right, at this point I'm going to go through a couple of higher level questions on this mechanism which crop up. Okay, now I've drawn out this haloalkane twice. This is 2-bromo, so meth, eth, prop, bute, 2-bromo-butane. If I was to carry out the elimination mechanism with 2-bromo-butane, I've got 2 options. So here's my hydroxide ion. That's come from sodium hydroxide or potassium hydroxide. And remember, the rule is the hydroxide ion has to attack a carbon which is next door to our halogen. So here's my halogen. I need to attack a next door carbon. And again, it's got 2 next door carbons. This one is next door, so it could attack one of those 3 hydrogens. But also, this carbon is next door, and it could attack one of those hydrogens. Now, these hydrogens are not the same. This is not a symmetrical molecule. We say it's an asymmetrical molecule. So I'm actually going to get a different product depending on whether the hydroxide ion attacks at this side onto one of those 3 or attacks here onto one of those 2. So I'm going to go through the 2 options that could occur. So let's say my hydroxide ion attacks on this side. I attack my hydrogen, mark number 1. The carbon-hydrogen bond goes into the carbon-carbon bond, that's mark 2. And then I kick off my halogen for mark 3. If that occurs, then I have a double bond between carbons 1 and 2. Carbons 3 and 4 have pretty much stayed intact as they are. I've got 2 hydrogens left on the end. Carbon 2 has 1 hydrogen, and carbons 3 and 4 have got all their hydrogens intact. So that is but1-ene, and as with last time, water is formed and a bromide ion is released. But it's just as feasible that a hydroxide ion could have attacked one of the hydrogens, which is on carbon number 3 of our chain, okay? When I say before that whether the hydroxide chooses to attack on this side or the other side, the hydroxide doesn't choose anything. It's not got a brain, it can't think for itself. It will just randomly collide with different parts of the molecule. So if it randomly collides with one of these 3, this reaction will occur. If it happens to just so collide with one of the hydrogens, which is on the 3rd carbon of the chain, the same mechanism occurs, so attacking the hydrogen, 1 mark. Electrons from the hydrogen-carbon bond go into the carbon-carbon bond, 2 marks. Kick off the bromine, 3 marks. But this time you will notice that the double bond forms between the 2 carbons in the middle of the chain. So carbon 1 is actually unaffected, that's still got 3 hydrogens attached. Carbon 2 has lost its bromine, but still has this hydrogen. Carbon 3 has lost this hydrogen, but has still got its other one. And remember, we've formed a double bond between the 2 there. And then carbon 4 at the end still has all 3 of its hydrogens attached. Plus H2O plus Br minus. So this has got the double bond in the middle of the chain. This is but2-ene. So if we carry out the elimination mechanism on a haloalkane like 2-bromobutane, I'm going to get a mixture of products. I'm going to get some but1-ene and I'm going to get some but2-ene. Now, you may also remember from your introduction to organic chemistry topic that alkenes exist in different isomer forms as well, different geometrical isomers called E and Z isomers. So but2-ene could also exist in 2 different formats. I could have but2-ene where the methyl groups are on opposite sides of one another. So here's the straight line down the middle of the molecule and my methyl groups are one up and one below. But it could also be that there's my double bond in the middle. It could be that both methyl groups end up on the same side. So here, because the methyl groups are on opposite sides, we'd call that the E isomer. Here, because the methyl groups are on the same side of the double bond, we'd call it the Z isomer. Okay, so from one combination of reagents, from my hydroxide ion with my 2-bromobutane, I could end up with 3 different products. I could end up with but1-ene, I could end up with E but2-ene, or I could also get Z but2-ene as well. Okay, so isomerism often crops up in the questions involving the elimination mechanism. Right, I've got a bit more of an extreme example now of how isomerism can play a part of the elimination mechanism. I have got a much bigger haloalkane here, so I've got a 6-carbon chain, I've got a chlorine and a methyl group on carbon 3, so this would be called 3-chloro-3-methyl-hexane. And I want you to imagine that we're going to carry out an elimination mechanism on this molecule. So I've got some ethanolic sodium or potassium hydroxide. There's my hydroxide ion ready to attack. What I want you to do is pause the video clip for a moment and think, how many different products could this molecule make? If my hydroxide ion can randomly attack this molecule and carry out an elimination mechanism, how many different products could it form? Pause the video and think. Right, let's go through. So I'm going to go through the mechanism 3 different times here. Remember, the rule is that our hydroxide ion has to attack a hydrogen which is on a carbon next door to where our halogen is. So here's our halogen. Here's the carbon that our halogen is attached to, and it has 3 carbon neighbours. This is a neighbouring carbon, this is a neighbouring carbon, and this is a neighbouring carbon, which means these 2 hydrogens could be attacked. It means these 3 hydrogens could be attacked, and it also means these 2 hydrogens could be attacked. And depending on which type of hydrogen our hydroxide ion attacks, then it's going to change what product we get. So I'm going to call this, well, let's call this carbon A, carbon B, and carbon C. If my hydroxide ion attacks one of the hydrogens on carbon A, we form the double bond in that position, and we kick off our chlorine there. So as a result, let me draw out the product. I'm going to have a 6 carbon chain, 5, 6. The double bond is between carbons 2 and 3. So that's my alkene group. Carbon 3 has the methyl group. And then I've got hydrogens filling in all the rest of the gaps. Okay, so that's one possible product. If my hydroxide ion attacks one of the hydrogens which is on carbon B, so I'm going to do this down here now, so one of these 3 hydrogens, we attack our hydrogen. Arrow number 2 always breaks the carbon-hydrogen bond, and the electrons go into the carbon-carbon bond where the halogen is attached. So it's going to go in to there, and then we're going to kick off our chlorine at the bottom. So again, this time if I draw out the product, 1, 2, 3, 4, 5, 6 carbons. Carbon number 3 is where the alkene group attaches onto our carbon branch. So 2 hydrogens up there, 1, 2, 3 hydrogens there, 1 and 2 hydrogens there. So there's the rest of our molecules. That is a different product. And then finally, what happens if our hydroxide ion attacks one of the hydrogens which is on carbon C? So let's go through that mechanism. Attack the hydrogen. The carbon-hydrogen bond goes into the carbon-carbon bond, and then that kicks off our halogen. And if I draw out the product of that, we've still got a 6 carbon chain. 1, 2, 3, 4, 5, 6. The double bond is between carbon 3 and 4. So 3 to 4, that's where our double bond is. And then let's fill in all the gaps. 3 hydrogens there. 2 hydrogens there. We've got the methyl group on carbon 3. Carbon 4 now just has 1 hydrogen. Carbon 5 and carbon 6 still have all their hydrogens intact. So we've got 3 different products, but then we need to consider whether these can exist as E and Z isomers as well. Now at this stage I should say, if you haven't done EZ isomerism yet, do not worry. We're going to move on to the alkene topic very shortly, and we'll reiterate the key points of EZ isomerism. But I know some classes will have done EZ isomerism as part of their introduction to organic chemistry topic, so we'll be able to have a go at this. So if I look at this molecule here, the criteria to have EZ isomerism is, do you have different groups attached to each end of the double bond? And in this example we do. If I draw the double bond here, The first carbon of the double bond has a hydrogen and a methyl group. Hydrogen, methyl group. The second carbon of the double bond has a methyl group and a meth-eth propyl group. Methyl and propyl, C3H7. Now, it could quite easily be that the methyl groups which are opposite one another here could be on the same side. So the alternative isomer for this C3H7 and CH3. Okay? Now, if we had to name these isomers, you need to pick, I'm going to skim over the rules slightly, but essentially you need to pick the heaviest group on each end of the double bond. So, on this end, a methyl is heavier than a hydrogen. On this end, a propyl is heavier than a methyl. So because the two heavy groups are on the same side of the double bond, this makes it a Z isomer. On this one, the methyl is heavy, the propyl is heavy on this side, and these are on opposite sides of the double bond. So that makes it the E isomer. Here, one carbon on our double bond has two of the same group. As soon as one end of the double bond has two of the same group, you can't have EZ isomerism. So this is the only version of this product. There are no EZ isomers here. And then finally, if we look at this one, this does also have EZ isomers. If I draw the double bond here, this carbon has got a methyl and an ethyl, CH3, C2H5. This carbon has got a hydrogen and also an ethyl group, C2H5. And just like last time, at the moment we've got the two ethyl groups which are on the same side of the double bond, but it could be that they form the other way around. C2H5, C2H5, CH3 and H. So just like my example up here, you need to pick the heaviest group on each end. So the heaviest group on this carbon, methyl or ethyl, is the ethyl. The heaviest group out of a hydrogen and an ethyl is the ethyl. So these are on the same side, so that's the Z isomer. The ethyl and the ethyl are on opposite sides, so that makes it the E isomer. So there are 5 possible products in this mechanism, because I could end up with the E and Z isomer of this product. This product there's just one version of, and then I could end up with the E and Z isomer of this product as well. Now this is quite an extreme example of how isomerism gets involved in the elimination mechanism, but it's good for you to see a full example of that. Okay, so just before I move on to the next bit of this topic, I just really want to reiterate this. This is mentioned in page 13 of your notepad. Now, page 13 on the notepad actually goes into a lot more detail than you really need. It goes into an in-depth comparison of what conditions lead to nucleophilic substitution, what conditions lead to elimination mechanisms. I'm just going to condense that down to the essential bit, which is the key bit that gets assessed in exams, which is to do with the solvent. So the conditions are the key. As soon as an exam question mentions it's an aqueous condition, aqueous means nucleophilic substitution. So that means if you've got haloalkane with hydroxide ions, they're going to swap places and you end up with an alcohol and bromide, or whatever your halogen is. As soon as it mentions ethanolic, you should be thinking elimination. I just think about the E's. Ethanolic means elimination. So as soon as you hear about that, then it means that our hydroxide ion and haloalkane aren't going to undergo a substitution, they're going to undergo an elimination. And elimination mechanisms always result in the formation of an alkene. Water is formed. Oh, I also need to add my bromide ion there as well. Okay, so ethanolic leads to elimination, and it always forms an alkene as a product. So think about all those E's. Ethanolic, elimination, alkene product. So make sure you drill that into your head, because there's a lot of scope to win marks on an exam question like this, but it's quite easy to lose marks as well. There have been several examples in the past where an exam question wants an elimination mechanism. A student might draw a perfect nucleophilic substitution mechanism which would get all the marks, but of course they don't get all the marks. They don't get any marks because it's the wrong mechanism. They need to do the other one. So make sure that's drilled into your head. Right, last bit of this topic, and this is a relatively short bit of the topic which you just have to learn. It just boils down to committing a few key facts to your memory. So it's to do with the ozone layer. So by all means refer to page 14, page 15 of your note packs on this. So you may not know, but the ozone layer, ozone is actually made up of oxygen. You've heard the term allotrope before. Allotropes are structurally different formats of different elements. So the main example of allotropes you've encountered are things like diamond and graphite and fullerenes, all examples of carbon. Well, essentially, ozone, the molecule O3, is an allotrope of oxygen. Oxygen typically exists as O2, but as an alternative, you can get oxygen which forms O3. And when it's in that format, we call it ozone. Now, ozone is found up in the very high levels of our atmosphere, between 15 and up to 50 kilometers above the surface of the Earth. And that layer of ozone gas is really useful for us because it absorbs loads of the UV radiation which comes from the sun. If the ozone layer was not there, there would be a lot more people getting sunburned, there'd be a lot more cases of skin cancer because that radiation really can cause a lot of damage. So the ozone layer does a lot of help for us in reducing the amount of UV radiation that gets down to the surface of the Earth. So this is a good thing. Now, you may have heard the term CFC. A CFC is just a shortened name for a chlorofluorocarbon. So it's a collective name for any organic molecule which contains chlorines and fluorines. So these are a couple of examples. So this is trichlorofluoromethane. This is difluoromethane. So these are examples of organic molecules which have chlorines and fluorines attached to them. So these are examples of CFCs. Now, several years ago, probably when I was at school, so 20 something years ago, CFCs used to be used in aerosol cans. They used to be used in fridges, freezers, and air conditioning units. Okay, aerosol cans, CFCs were used as an accelerant, and CFCs were used as the cooling agents inside fridges, freezers, and air conditioning units. And they did a really good job. The problem was when people disposed of these things, so when they threw away aerosol cans, when they'd finished, when they're having a new kitchen installed and they were throwing away their old fridge, CFCs can leak into the atmosphere. And when CFCs are released into the atmosphere, they go right up to the top of our atmosphere and they undergo an initiation reaction. And when I say an initiation reaction, I mean very similar to the initiation reactions we see in free radical substitution mechanisms. So you remember when we have Cl2 and it splits up into two chlorine radicals, for example. That's in the presence of UV light. So I want you to imagine that we've got this CFC, so this is difluoromethane. It's been released into the atmosphere, and high up in the atmosphere where it's exposed to lots of UV light, this can break into free radicals as well. So it must be that this bond is broken and it forms a chlorine radical and this chlorofluoro radical. Okay, now this bit I'm not worried about for now. The chlorine radical is the problem. It's the chlorine radical that can damage the ozone layer. And let me explain how. Now, the next bit is the key bit of this section of the topic. These are just reactions that you just need to learn, okay? So, ozone made up of O3. If up in the atmosphere it collides with a chlorine radical, the first thing that occurs is that the chlorine radical will take an oxygen off this. So O3 will turn into O2, and in doing so it makes a ClO radical. This is called a chlorate radical. Okay, so already an O3 molecule has been turned into an O2 molecule. So this is a bit like a propagation step, if you like, because we start off with a radical, we form a new radical in the end of that reaction. In step 2, that chlorate radical that we've just formed collides with another O3 molecule. And what happens is these 3 oxygens and this 1 oxygen form 2 more lots of O2. So we've got 4 oxygens there. We now have 4 oxygens there. And the chlorine gets reformed back to its original state of a chlorine radical. Okay? So these 2 stages are how the ozone layer gets broken down. And you could be asked, what's the overall equation? So if you're asked the overall equation, all you have to do is add up everything on the left and everything up on the right. So I've got O3, I've got a chlorine radical, I've got a chlorate radical, and I've got another O3, so I'm going to put a 2 in front of that one. On the right hand side, I've got O2, I've got a ClO radical, a chlorate radical, I've got 2 more O2s, so I'm going to turn that into 3 lots of O2, and I'm going to have a chlorine radical. And as is always the case with equations like this, let's do some cancelling. I've got a chlorine radical on one side and on the other side. I've got a chlorate radical on one side and on the other side. So it just boils down to 2 lots of O3 end up forming 3 lots of O2. Now, of course, the product isn't dangerous. Oxygen is a good thing. So we're not worried about the product forming being dangerous. The issue is the O3 molecules form this nice protective barrier in the top of our atmosphere, and the more chlorine radicals that were formed in the top of the atmosphere means that the more ozone is broken down. So you may have heard the term, there's a hole in the ozone layer. That's because chlorine and fluorine radicals could break down the ozone molecules into O2 molecules. And the worst thing about this reaction is, after our chlorine radical has broken down O3 molecules into O2 molecules, the chlorine radical is regenerated at the end. You could say that the chlorine radical is acting as a catalyst, which unfortunately means this is now free to go and catalyze the same reaction over and over and over and over again. So a very small amount of chlorine radicals in our atmosphere can cause a significant amount of damage. So since this was a big problem about 20, 25 years ago, there's been a lot of regulation on the use of CFCs. So CFCs can no longer be used in aerosol cans. They can no longer be used in refrigeration units. And so the problem has pretty much been fixed. The ozone layer does regenerate, it does fix itself. So where there were patches in the on the Earth where there were holes in the ozone layer, most of those have been patched up now. But this is a reason why chlorine and fluorine radicals were a problem for quite a while. Okay, so at this stage, you should now be in a position to have a really good go at the majority of the rest of the question pack. So again, let me put this on my screen just to explain fully. So we should be up to task 12 in the question pack. So comparing substitution and elimination. So outline the mechanism for the elimination of 2-bromopropane. So you should be able to have a go at task 12 and 13, again on those mechanisms, and 14, thinking about that. We then move on to a few tasks to do with the depletion of ozone. So that's what I just mentioned in the previous bit of the video, how CFCs can lead to the depletion of the ozone layer. So you can have a go at all tasks now up to and including task 20. And you can also now have a go at all of the past paper questions. Now let's just have a quick check. There's a significant number of them. So we've got, it goes up to past paper question 12. I have set some of these previously, so you'll have already done some of the ones which involve free radical substitution. But this is going to be a fairly significant ongoing task now. I've mentioned previously that I'm going to start trying to get into running some lessons on Microsoft Teams. So here's the deal. I want you to carry on and complete as much of this question pack as possible. All tasks, all past paper questions. Once I've got my head around Microsoft Teams, which hopefully will be towards the end of this week, I will set up a Microsoft Teams lesson where I will go through some of this work. I'll go through some of the problem questions. Now, that doesn't mean to say the deadline for completing this booklet will be the end of this week. I'll give you a fair chunk of time to do it. But if whilst you're having a go at some of these tasks and questions, there are bits that you get stuck on and you specifically want me to go through those during the Microsoft Teams lesson, you can send me an email. Hi, sir, I'm really stuck on past paper question number 7, and I'll factor in that feedback when I'm running the Teams lesson, hopefully later on this week. Okay, so I've not set an official deadline yet. Just for now, keep plodding on with these tasks, and I will be in touch in due course once we can set up a lesson on Teams to go through some specifics and deal with problems that have cropped up along the way. Okay, as ever, any individual questions along the way, send me an email. I will happily help out as best I can. Okay, take care. See you soon. Cheerio for now.